Yes.
Have you seen 2001: A Space Odyssey?
Multiple occasions, yes. Yeah, what's that? Oh, really? What I often find is that when I show it to groups of students, they're like, they could do those special effects in 1968? Yeah, I read the book too, I read the novel. It's definitely got a LSD trip at the end, essentially, but yes. Yep.
Have you watched The Contact?
Yes, as a matter of fact. And I spoke with Carl Sagan once. So,
Wow.
yeah. I spoke with Carl Sagan once.
Excuse me?
Yes. Well, I talked to him about nuclear winter because he was an alum of the University of Chicago where I was in grad school, and so he came back for a reunion. So I had to talk to him. And then I tell my mom, and she goes to her friends like, my son talked to Carl Sagan. And they're all, who's Carl Sagan? I'm like, rubes, bunch of rubes. I couldn't believe it. Yeah, but yes, But yeah, that was cool. Yep, indeed. All right, let's see. Where were we? Okay. Now we're going to talk about the equivalent one-body problem. We've been talking about orbits and all that. And, of course, we've got two objects orbiting one another, but we can turn it into an equivalent, what we call one-body problem, which simplifies everything. Unfortunately, that's as far as we can go. If you have three bodies, well, you're sunk. You cannot get an exact analytic solution for any more than two mutually interacting gravitating bodies. But you can do it for two, and so let's do that here. So the equivalent one-body problem. So, we can simplify the gravitational two-body problem, two objects orbiting their common center of mass, by replacing it with an equivalent one-body problem. We get everything we need from the one-body problem. It can be translated back into the two-body problem. So, big picture, what we're doing is, what are our degrees of freedom here? We've got three position components for the first body, three position coordinates for the second body, three momentum XYZ components for the first body, three momentum components for the second body, so 12 in all, and we're going to replace that with the position and momentum coordinates of the center of mass of the system plus the position and momentum coordinates of what we call the reduced mass of the system relative to the center of mass. So I'll write all that out and then we'll explain how that works. What we are doing is to replace the three components of the position and momentum of each particle the three components of the position and momentum of each particle So that's 12 degrees of freedom in all. Twice as many as there are, degrees of separation from Kevin Bacon, right? That whole business. 12 degrees of freedom in all. With the three components of the position and momentum of the center of mass, so there are 6 degrees of freedom so far. And the position and momentum of the reduced mass big letters because we're introducing a new term here, the reduced mass, and we're going to use the simple Greek letter mu, and it's equal to m1 m2 over m1 plus m2 along with the relative displacement in other words, the position of the well, what we're going to say the relative displacement is R2 minus R1, how the two masses are linked to one another, the position vector of the second one relative to the first one, if you will. The relative displacement vector equals R2 vector minus R1 vector. Of course, it's arbitrary which particle we call 1, which particle we call 2. So that's up to us, and we could do everything in the opposite order if we wanted to. But we just have to make a choice and stick with it. So that's the other 6 degrees of freedom. While you're all catching up in your writing, I'm going to go grab the laptop because I want to show you a visualization of the two-body problem after it boots up and is ready and all that kind of good stuff. Forgot I was going to do that, otherwise I had it ready to go already. Oops. Extra weight on my shirt now, my microphone. Got a fancy microphone attached to the camera back there now. What questions do you have at this point? Twisted my knee. Ow. Okay. So, let's remember how we define the center of mass. So let's make ourselves a coordinate system here. It's not really necessary, but we'll have some origin. We do want to have an origin here. And let's say here is M1 with position vector R1. And let's say here is M2 with position vector R2. Then the relative displacement, R2 minus R1, remember the rule is that points from the back vector to the front vector, so to speak. So R2 minus R1 is that vector right there. R is R2 minus R1. So that's the relative displacement. It's where M2 is relative to M1. And the center of mass lies somewhere on the line joining the two particles. Remember, that's always true for a pair of particles. The center of mass always lies somewhere on the line joining them. And it lies closer to the more massive one. And so I haven't specified masses here, but let me just kind of arbitrarily say, all right, let's suppose that in this case, there's the center of mass right there, and we're going to call capital R the position vector of the center of mass. So remember the definition of the center of mass is that its position vector relative to our origin is capital R is equal to, by definition, M1R1 plus M2R2 divided by M1 plus M2, or in other words, it's a weighted average, if you will, of the position vectors of the two masses, weighted by the masses. So as M1 gets bigger and bigger relative to M2, the center of mass approaches the location of M1, right? In other words, if M1 was really big compared to M2, then in that limit, this becomes practically just R1 because it would be roughly M1 over M1 times R1 because M2 is very small under that assumption. But if M2 gets very large, it approaches M2, so it's on the line joining them. If they were equal masses, it would be halfway between them. I think I'm going to erase over here. Is this erasable? It's going. All right, now I'm going to tell you some stuff which you've probably seen before, but repetition is the key to learning. The more you see something, the more it sticks. So let's derive fun things like the fact that if you have a system of particles and it's a closed system, they're only interacting with one another. Well, actually, it doesn't have to be a closed system. I take it back. If you have a system of particles, and you get to decide what is your system of particles, the center of mass moves as though it were a single particle with the total mass of the system and under the net external force applied to the system. So that if there's no net external force applied to the system, then the center of mass moves like a particle whose mass is the mass of the system and moves under the influence of no force whatsoever, meaning that if it's a closed system, nothing else is interacting with it, how does the center of mass of the system move? It moves like a particle whose mass is the total mass of the system and for which there's no force on it. If a particle has no force on it, how does it move? It moves It was at a constant speed, but also
In what direction?
Yeah, in a straight line at constant speed, right? If there's no force on something, it moves in a straight line at constant speed.
I was going to say it doesn't move, but...
No, but well, that's the special case, right, of no speed, right, zero speed. But in general, it moves in a straight line at constant speed, right? Because if there's no net force, there's no acceleration of the center of mass. No acceleration means the velocity is constant. Well, what is constant velocity motion? It means that both the direction and the magnitude of the velocity are constants. Well, if the direction is constant, straight line. If the magnitude is constant, what do we call the magnitude of the velocity? That would be the speed. So straight line at constant speed is how something moves if it's got no net force on it. That's true for a single particle. For a system of particles, the center of mass exhibits that behavior. The center of mass behaves as though it were a particle. It moves just like a particle would whose mass is the total mass of the system. And it is operated on by the net force applied to the system. Now, if you have a closed system, a bunch of particles interacting with one another, will there be a net force on the system? If so, why? If not, why not? If you got a bunch of particles, they're just interacting with one another, nothing external, will there be a net force on the system? So what does Newton's third law say about the force that one particle exerts on another particle and vice versa? Equal and opposite, right? So if particle 1 exerts a force on particle 2 exerts an equal and opposite force on particle 1. So if I add those two forces together, what is the result? 0. So if you have a system of particles that's not interacting with anything else, only with one another, internal forces cancel in pairs because of Newton's third law. So the sum of the forces on all the particles is 0 because of Newton's third law. Only external things can produce a net force on a system. So if you are out in outer space, you cannot move your center of mass because any part of your body that exerts a force on another part of your body, well, that other part of your body exerts the equal and opposite force on that first part of your body. Those forces cancel in pairs. You cannot exert a net force on yourself. Nothing can exert a net force on itself, right? If I walk across the room, what's exerting on the for review, so to speak, right? If I walk across the room, what's exerting the force on me that lets me do that? Gravity would just make me fall to the floor. So what's getting me to, right now, not moving. I do this. Now I'm moving. What's exerting the force on me that allowed me to move like that?
Force by the ground in the opposite direction.
Yeah, so the ground is exerting that force on me. What kind of force is it?
I said normal.
The normal force just keeps my center of mass from falling. I got to move horizontally here, so that's not a normal force doing that. It's a sideways force. What kind of force is that going to be from the ground? Friction. It's friction. It's contact friction. I mean, it's static friction is what's exerting that force on me. If I were on super slippery ice, I would not be able to move myself horizontally because the ice would not be cooperating and exerting a force horizontally on me. Okay, you're in a car and you drive the car. What's exerting the force on the car that gets the car to move? You hit the gas, the car accelerates. What's exerting the force on the car that's causing that acceleration? The road, right? It can't be the car itself because internal forces cancel in pairs, right? You win money this way. You bet people, they're going to tell you the engine is exerting the force on the car that's making it move. Everybody knows that. Engine's part of the car. Whatever force the engine would exert on the rest of the car exerts an equal and opposite force on the engine. So it ain't going anywhere based on that. It's the road that's exerting the force on the car that allows it to move. This is everywhere, right? And again, if the car were in outer space, what would stepping on the accelerator do for you? Make the wheels spin, but would it get the car to go anywhere? No. If it was on super, super slippery ice, you're not going anywhere, right? You just spin out. It's got to be the road that's exerting that force. right? So keep this in mind. The way that you move your body is not anything internal. It's your body exerts forces on your environment so that, by Newton's third law, the environment exerts equal and opposite forces on you, and that's what allows you to move yourself. And that's true not just for you, but it's for anything, right? The only way anything can change the location of its center of mass is by exerting forces on its environment, on other things, which then cooperatively exert equal and opposite forces on it, and those are what make it move. It's only external forces that can make something move. Nothing can ever move due to internal forces. So somewhere along the way you've heard all that before, but I'm also getting the impression, it's not really fully in your consciousness, so make that fully in your consciousness. That's a fundamental fact about the way the world works. Tell your friends. Bet your friends. Make money on them. Send them to me when they claim it's truly the engine. Payday. All right. What questions do you have? Comments? Observations? Yes?
Over there,
Yep.
if we did not have an origin, I mean, if we did not draw that diagram, would we consider the observer to be over there to calculate the R?
So none of this, this is just you could pick an origin anywhere and do this calculation, but the location of the center of mass is intrinsic to the two particles. In other words, it's on the line joining them, and it's closer to the center of, it's closer to the larger, I should say more massive object. The location of the CM in space, that's just a property of the system itself. It's up to us where we draw the origin. R1 would change, R2 would change, capital R would change, but wherever the origin is, then capital R will be a vector from that origin to this same point in space. The point in space that is the center of mass is independent of the choice of origin. Yep. Okay, let's generalize this to an arbitrary number of particles. So, in general, and this is where I'm going to prove all those things that I just said before about the system center of mass acting like it's a particle with the total mass of the system, and you can't exert a net force on yourself and all that kind of stuff. I'm going to make that formal here. In general, for n number of particles, n particles in a system, we have that the center of mass, we just generalize that definition. In other words, we make it M1R1 plus M2R2 plus M3R3 plus M4R4 plus M4,973,642,212 M, whatever I just said, divided by the sum of all the particles' masses. So, in general, the center of mass vector is defined to be the sum from I equals 1 to the number of particles of M sub I R sub I divided by the sum of the masses of all the particles, right? In other words, that formula over there is just this formula for n equals 2, so that there's only 2 terms on the top and 2 terms on the bottom. So we generalize by making it a weighted sum over all the masses in the system divided by the total mass of the system. And so we say this is the sum over I. I'll just suppress the up to n there. It's just understood there's some number of particles n of the MIRI divided by capital M, where M is just the total mass of the system. It's add up all the masses. It's the total mass of the system. Well, notice that says that M times capital R is the sum of the MIRI. So the total mass of the system times the position vector of the center of mass is equal to the sum for all the particles in the system of the MIRI. add up mi times ri for every particle, and the result is the total mass times the position vector of the center of mass. And again, one can show that the point in space represented by the center of mass is independent of the choice of origin. You'll always get the same location in space. Of course, with different origins, the vectors themselves will be different, but the position vector but the position itself in space of the center of mass is always exactly the same. Two, 4, 6, 8. Time to differentiate with respect to time. So, we're going to use the notation that a dot over a symbol means its time derivative, very common. How many of you have taken mechanics already? Yeah, so you probably saw this in mechanics, I'm guessing. But again, repetition is the key to learning. So, we can say then, since MR is the sum of the MIRI, take a dot on both sides. MR dot is equal to the sum of the MIRI dot, right? Because the derivative of the sum is the sum of the derivatives. So I just take the sum of all those derivatives right there. Or if we define capital V to be R dot, the velocity of the center of mass, oh man, I'm that guy. Hush. There we go. Okay. Or capital M, capital V vector is equal to the sum of the MI VI, because RI dot is the velocity vector of particle I. Well, what this is saying is what? What is MV for a particle? What do we call MV for a particle? Yes, the momentum, right, that's the momentum. Or in other words, the center of the total mass times the velocity of the center of mass is the sum of the momenta of all the particles. Right? So add up all the momenta of all the particles. That's the total momentum of the system. And it's equal to the total mass of the system times the velocity of the center of mass. In other words, the center of mass acts as though it's a single particle with the total mass of the system and with moving with velocity v such that mv is the total momentum of the system. So if we say capital P is capital M, capital V, we see that in terms of calculating the system momentum, we can replace the system with a single particle of mass capital M moving with the velocity of the center of mass. We can replace the system with a single particle of mass capital M total mass of the system, add up all the masses. Moving with the velocity of the center of mass. Because V is R, capital V is capital R dot, so that's the velocity the center of mass is moving with. That's a really neat result. That's a great simplification. What questions or comments or observations do you have? Tears of joy. What a beautiful result that it is. Two, 4, 6, 8. Time to differentiate again. Let's take another time derivative. Another differentiation. Why stop there? Another differentiation yields capital P dot, the time derivative of the system momentum, is equal to the sum over all the particles of the time derivatives of their momenta, but for any given particle, what is its rate of change of momentum? It's equal to the what on that particle? What is fundamentally such a fundamental law in Newtonian mechanics? A particle's rate of change of momentum is the on that particle.
Force.
The force. It's the force on that particle. It's the force. Oh my God. Somebody said acceleration? Yeah, it's the force on that particle. Yes. Don't worry, you're off camera. Nobody knows your voice in 50 years, right? So, because I'm sure this will be watched 50 years from now. So, so this is the sum. No, actually, it's going to be worth big bucks, because you'll be this Nobel Prize winner, and people are going to be like, yeah, but what about that time he thought that, All right. Hey, it happens to the best of us, right? Okay, so equals the sum of the forces on all the particles, right? Because remember, right, so yeah, F is ma, and that's how you always keep hearing it all the time. But it's really better to think of it as, well, note that that's equal to d dt of mv, right? Because A is dv dt, so that's dp dt. And in some ways, that's kind of a better way to think of what force is. It's rate of change of momentum. Because momentum is a more fundamental physical quantity than, kind of like ma, yeah. All right. So you add up all the forces on all the particles, and that's the time rate of change of the system momentum. So the rate of change of the system momentum is equal to the total force on the system. So add up all the forces on the system, and that's the rate at which the total system momentum changes. That's the rate at which the total system momentum changes. Or in other words, it's also equal to the mass times the acceleration of the center of mass, because v dot we could call a, the acceleration of the center of mass. Ooh, gotta say it there. So I can do that too, where A there is V dot. A is big V dot. Just kind of almost as an aside there, but that's there too. But if we look at the total force on this system, let's look at Newton's third law here. By Newton's third law, for a closed system, no interactions with anything external. And again, keep in mind, like if you're thinking like, well, what makes the system a system? You can collect any set of particles together and call them your system. That's completely up to you. But if your collection of particles you've decided to call your system has no interactions with anything external, we say it's a closed system, then the internal forces, all right? See if you got what I was saying. What can we say about the internal forces? If we add up all internal forces, that I is not internal, it's just the ith particle. But in other words, if all the forces are internal forces, there's nothing external on the system applying any forces, what's the sum of all those internal forces? Zero, because they've canceled in pairs. Then the internal forces cancel in pairs. So that the sum of the Fi is equal to 0, and that says P dot is equal to 0, because P dot is the sum of the Fi. P dot is equal to 0. So if P dot is 0, P itself is P itself is constant. It's constant. P itself is constant. P itself is constant. Or in other words, the center of mass moves in a straight line at constant speed. The C of M, center of mass, moves in a straight line at constant speed. A very fundamental fact. So, okay, I'm not going to do it, but if I were to be up on a diving board, right? I'm the great diver here. I'm going to dive off and do whatever divers do, I'll make something up. 2.5 somersault with I don't know, whatever, right? So I jump off and amazing, things I do on the way to the water's surface. And, oh my God, hardly any water even splashed. Wow, it was amazing. Describe the motion of my center of mass on the way down. What's that? Well, is there a force on me on the way down?
Yes.
It is. There is. What's that force? Gravity. If I throw a ball, how's the ball move? Yeah, it does a parabola, right? It does a parabola. Center of mass of the system moves exactly like a single particle with the total mass of the system moving under the net external force on the system. So my center of mass moves exactly like a single particle with my mass moving under the influence of gravity. So what does my center of mass do? It just follows a parabola. No matter how amazing and impressive the diver is doing things, their center of mass just goes, right? Just simple parabola, just like a ball would, right? Because, as part of the power of the center of mass is doesn't matter what all the particles are doing individually, the center of mass moves like a single particle under the net external force applied to the system as a whole. Ooh, ah. All right. So, questions, comments, observations? So if we've got a closed system, the center of mass just moves at a straight line constant speed. So if you're in outer space, you'll move in a straight line constant speed no matter what you're doing in terms of et cetera, et cetera. Now, you could move yourself off that by expelling mass, like you have a rocket thruster or a fire extinguisher, or not a good idea, you take off one of your space gloves and throw it, center of mass of the system stays still moving in a straight line at constant speed, but that means that you and the rest of your spacesuit will have had a force applied to them by the glove that you threw, and so you're able to change your motion that way. But if you stay with the original system, you plus the glove, that center of mass is still moving in a straight line at constant speed. Right? Okay, so consider our two-body problem again. If those are the only two things we're worried about, if they're not interacting with anything external, their center of mass moves in a straight line at constant speed, so why not just jump into the frame of reference that's riding along on the center of mass, and then just watch how everything moves relative to the center of mass. And so that's what we'll think in terms of doing here. So, that last point, that the center of mass moves in a straight line at constant speed for a closed system, this means we are free, I tell you, we are free to ride along on the center of mass, so to speak. To ride along on the center of mass and do all our calculations in an inertial reference frame which has the center of mass at its origin. Do all our calculations in an inertial reference frame that has the center of mass at its origin. And so then our two objects, we will see they'll just both orbit around the center of mass, and in general, in some arbitrary inertial frame, they'll be doing that at the same time the center of mass is moving along at a straight line at constant speed. But we can jump into a frame where the center of mass is stationary, and then everything's just moving around that fixed stationary origin. That's a choice we can make. You might have seen these videos on YouTube and so forth where they'll be like, oh, everything you learned about the solar system is wrong. What's really happening is then they show these videos where everything is making spirals, right? Have you seen those things? And, well, they're not wrong, but they're not fully right either. In other words, true, the center of mass of our solar system is orbiting the center of the Milky Way galaxy, and for quite a while, that's a good approximate, you have to make quite a bit of an orbit for you to start to see the arc, so not a bad approximation that relative to the center of the galaxy over short time periods, center of mass of our solar system is moving along through space in a straight line at constant speed, and then the orbits of the planets are nearly circles around that, so that means there are these corkscrew thingies or whatever. But the claim that that's correct and putting everything just orbiting a stationary center of mass is wrong. You're perfectly fine to jump into the frame where the center of mass isn't moving. That's not wrong. Now, that won't last because we are accelerating around the center of the galaxy. But in other words, you could just as well pick a frame where everything's going like this, because you're in a frame where the center of mass is moving this way in the plane of a planet's orbit. And so it's making curlicues. All the frames are equally good, so those videos always kind of get me because they portray it as though, here's this big revelation. You were today's old when you realized that everything you were told about the solar system is a lie. No, it isn't. It's just that you could be in other frames of reference than maybe you thought of before, but the one you're taught isn't a lie. It's perfectly fine. Glad I could get that off my chest. All right. Questions, comments, observations? Well, we have a few more precious minutes before break. We don't want to waste anything here. So, one more thing we can say here before our break is, it cannot be true that, for example, the moon orbits a stationary Earth. Now, there's the lie, right? If you get told that the sun is sitting there at the center and everything's going around the sun. That can't be right, because is the sun of infinite mass? No. Do the planets exert gravitational forces on it? Yes, they do. If the sun is not of infinite mass, must it accelerate under those forces? Yes, it must. So the center of mass of the sun executes this complicated motion around the center of mass of the solar system as a whole. And because of the influence of Jupiter and Saturn, the center of mass sometimes is actually outside the surface of the sun. It wobbles a bit around the center of mass of the solar system. This is the key to discovering some exoplanets. In other words, some exoplanets are discovered by the gravitational redshift and blueshift of the star caused by the fact that a planet is tugging on it, making it orbit the center of mass of its system. And so if we have sensitive enough Doppler measurement instrumentation, spectrographs, we can detect that, and that's how the first exoplanet around an ordinary star, 51 Pegasi, was discovered, was from the Doppler method like that. So that's the lie, is that the sun is sitting there stationary and all the planets are going around it. There's no frame in which the sun is stationary, no inertial frame. You'd pick a non-inertial frame, but no inertial frame of reference where the sun is stationary and everything is going around it. Or as I'll put just from the notes, because it cannot be true that, for example, the moon orbits a stationary Earth, for then the center of mass would orbit Earth's center, which would be accelerated motion. It cannot. It just can't. It cannot be true, I tell you, that, for example, e.g., the moon orbits a stationary Earth, that's a lie that you're told when you're in school. It's not really a lie, it's a simplification for your young mind. But many minds get old and never get told that that was a simplification for their young minds. The moon orbits a stationary Earth because then the C of M would orbit Earth's center. Right, because the C of M is always on the line between Earth and the moon. So if the Earth were stationary, the C of M would move around the Earth as the moon orbited us. But that would violate Newtonian physics. Then the C of M of the Earth-Moon system would orbit Earth's center which is accelerated motion. That would be accelerated motion. But if you think of the Earth-Moon as a closed system, their gravitational forces on one another cancel. And the center of mass, therefore, should not be accelerating. Right? So that cannot be. Both Earth and the Moon orbit their center of mass. Both Earth and Moon orbit their center of mass. And meanwhile, the center of mass orbits the sun. The center of mass of the Earth-Moon system makes a nice orbit around the sun, while Earth and Moon orbit around the center of mass of the Earth-Moon system. Break time. Oh yeah, just leave early. Don't just go.
Show up there late.
Oh, okay. Cool. Okay. So, we're going to revisit Kepler's laws. Kepler said the planets orbit the sun with the sun at one focus and all that kind of business. Well, the sun is much more massive than any planet in the solar system. Jupiter is like 300 plus times Earth's mass, and the sun is about 1,000 times Jupiter's mass. So it's not a terrible approximation to say that the sun is sitting there with the planets orbiting it. Of course, as I mentioned, actually the center of mass can actually lie outside the sun sometimes. But now, let's get it right. Let's do Kepler's laws for the two-body problem, for just two objects orbiting one another. And so we will have Kepler's first law revisited, and then we'll demonstrate it up there. Kepler's first law revisited. The new improved Kepler's first law. You liked it before, you'll love it now. Says, both objects in a binary orbit one another about the center of mass in ellipses, with the center of mass occupying one focus of each ellipse. So they both orbit on an ellipse with the center of mass at one focus. Not that one's at the center, not that one's at a focus and the other's orbiting it. They're both orbiting on ellipses. The center of mass is a focus of both ellipses. Both objects in a binary binary system orbit the center of mass. Orbit the center of mass, C of M, I'll just keep saying now. Orbit the C of M on ellipses, with the C of M occupying one focus of each ellipse. And furthermore, both ellipses have the same eccentricity. They both have the same shape, not necessarily the same size. They both have the same eccentricity, and their semi-major axes lie along the same line. And we know the center of mass is always on the line joining the two objects. So therefore, it's always true that the line joining them passes through the center of mass and connects the two of them. The line joining them at all times passes through the center of mass. It has to, because the center of mass lies on the line joining them. So the line joining them at all times, passes through the center of mass. Again, that's, it's just because, well, that's what the center of mass does through the center of mass. So in other words, if you know where one of them is, you can find the other one by just drawing a line through the center of mass to where it intersects the orbit of the other one on the corresponding part of the orbit, and there it is. There's where the other one would be. Best way to illustrate that is with the University of Nebraska's Class Action app, which does all kinds of cool astronomical simulations, right? Like the one I was doing before for Kepler's laws. Here's for a binary system. So for those who can't be with us, I will turn the camera to the screen and zoom on in so that they too can enjoy this glorious gloriosity here, because that's the technical term, glorious gloriosity. All right, let me get the lights down. Let's see, these are switch right there. Yeah. Okay. So here I've got a case where both these stars are same mass as the sun, and I made them the same radius as the sun too. Well, even for kicks, I made them the sun's surface temperature, 5770 Kelvin. I can make them anything I want. And I've dialed up the eccentricity to the maximum it'll let me get away with, 0.6, and they're 10 solar radii apart. And so now I can start the animation and watch what they do. It's positively mesmerizing, I tell you. Whee! Because they're also obeying Kepler's second law, sweeping out equal areas in equal times. But now it's the line joining the star to the center of mass that is sweeping out equal areas in equal times. Whee! Now, I can have plenty of fun here. In other words, that's just one particular eccentricity. I actually can do it as they're moving, but no, I won't. I'll just stop the animation there. Let's dial down the eccentricity, and you get something like this. And again, notice, at any given moment, the line joining them goes through the center of mass. And so they're on corresponding kind of, parts of their orbits with the line joining them always going through the center of mass. If I make the eccentricity small enough with this equal mass case, if I get it down to 0, they're on an identical circular orbit just around one another there. But I could also change the masses. So which one will be closer to the center of mass, the more massive one or the less massive one? The more massive one will. So let's make star 2 more massive. Let's dial up the mass of star 2. There we go. I'll just keep it the same radius because it doesn't care about that physics. So there we go. So now in that case, again, the line joining them always passes through the center of mass, so they're always on opposite sides of the center of mass, and they're both on circular orbits in this case, so that could happen. If I dial up the eccentricity, then I can get, so this one I need to even be more eccentric to get them to, well, okay, so here's one possibility. La, 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 wee. I can't help myself. I have to say wee when they're doing that, yes?
So this is only for orbiting each other?
So this is a binary star system.
Okay.
And a binary star system, they will both orbit their mutual center of mass.
So sometimes that'll happen with one guy's in the middle and another one's over.
Yeah. Oh, absolutely. There's binary star systems that they can do whatever delights you. I mean, there's all kinds of possibilities here. Yes. No, not necessarily. Not necessarily. Yeah, they can definitely. Now, if there's significant tidal interaction, the orbit tends to circularize. As we will see, we'll show that the orbit will tend to circularize, because that's the minimum energy orbit for a given angular momentum. And the system will conserve angular momentum, but it can radiate away energy. But no, you can have all kinds of crazy configurations for a binary star system. And let's see, I can try some different, let's see, can I just reset everything? Oh, presets, how about student guide examples? I don't know, doink, what's that? Oh, okay. Now, so now we're in the plane of the orbit, and I'm going to change the orbital inclination to look down from above. See, ooh, we can like get eclipses, right? If you have an eclipsing binary, then they're passing back. Oh, these don't quite eclipse, but if we are closer to the, where's the inclination? If we're closer to the plane of the orbit, well, then it can be like peekaboo, right? Peekaboo, right? If we're like right in the plane of the orbit, why then it can be big time peekaboo. Peekaboo. If one of them is a tiny little planet, and it is much darker, lower surface temperature than the star. So I can't quite do that, but oh look, it's a planetary transit. Right there, right? Yeah, see, right? Actually, this is a star transit in this case, but I'm kind of doing a planetary transit there, right? It's the same kind of idea. Let's get the inclination up again, yeah, small again, because it's the orbital inclination. Here's called 0. We're looking down on the orbit. And let's see, let's make one of these suckers really massive compared to the other one. And let's get us a good eccentricity going here. I want the orbits to cross here. What do I got to do here? Let's see. Yeah, there we go. So, right, so we can get something like this too, where whee, and so on and so forth. So you name it, right? You can have fun kind of configurations there. Okay? Questions, comments, observations? I'm just going to leave that there to mesmerize you as I can. It's maybe a mistake. You'll be like, wait, what did you say, Dr. Harmon? But anyway, okay. So, see how much restraint you can show to not be totally, but I have to point this way. So my future audience will need less restraint because it'll be off on the side of their view. Look away, look away. Zoom out. There we go. Okay. So that's a small, that's a white dwarf or something. It's actually the more massive one, right? Even though it's got the smaller radius. So, just to get you thinking there. All right, let's see, where were we? Okay, with the origin at the center of mass, the origin of our coordinates at the center of mass, we have m1r1 plus m2r2 equals 0, because normally we divide by m1 plus m2, so we could put over m1 plus m2 for the usual definition of the center of mass, but then we could just multiply through and it's this 0 here, so you just, in other words, just m1r1 plus m2r2 will be equal to 0. All right, so r equals m1r1 plus m2r2 equals 0, because again, normally in the definition of the center of mass we divide by m1 plus m2. Okay, multiply through so that that 0 eats it, and we just need to worry about that. Okay, so this says that m1r1 is equal to minus m2r2. Or in other words, so one thing to note here is this is saying relative to the center of mass, that they're on opposite sides of the center of mass. This minus sign says they're on opposite sides of one another. And this is what tells you that the center of mass is along the line joining them, right? In other words, relative to the center of mass, you've got, here's one of them, here's the other one. It must be in the other direction because of that minus sign right there. So R1 and R2 are pointing in opposite directions, and therefore the center of mass is on the line joining the two masses. That's how you know that. So M1R1 is minus M2R2. Taking magnitudes, this says that M1 times the magnitude of R1 is equal to M2 times the magnitude of R2. Take magnitudes, you don't have to worry about the minus sign anymore. Or if we just call R1 the magnitude of vector R1 and R2 the magnitude of vector R2, this says that R2 over R1 is equal to M1 over M2. Actually, I'll just put it the same way I did in my notes with flipped around from that. So R1 over R2 is equal to M2 over M1 at all times. We didn't assume any particular time we were doing this evaluation at. So the ratio of their distances from the center of mass is the reciprocal of the ratio of their masses. Right? So in other words, if star 2 is twice the mass of star 1, star 2 is half as far from the center of mass as star 1, etc. So again, I'll note here, I'm making R1 and R2 be the magnitudes of those vectors, R1 and R2, that connect their positions to the center of mass. So this is saying the one that's more massive is close to the center of mass, right? If M2 over M1 is 10, R1 over R2 what do I say? If M2 over M1 is 10, R2 over R1 is a tenth, right? In other words, the more massive one is closer to the center of mass and vice versa. In particular, there is a moment when R1 is equal to A1 and R2 is equal to A2 when they're on their semi-minor axes of their ellipses. Remember that R is equal to A at those moments. So we can also say that A1 over A2 is equal to M2 over M1. In other words, the larger mass moves on the smaller orbit, which is what we said. And of course we know that because the center of mass is closer to the more massive one. So the larger mass moves on the smaller orbit. A1 and A2 are the semi-major axes of their two ellipses. I hope I was able to erase this. Okay. I'd be like, wait, let's go to the tape. And then of course, it's not a tape. Sometimes people say, let's go to the tape. What tape? It's an SD card. Let's go to the SD card. Okay. Questions, comments, observations? I'm sorry. What questions, comments, or observations do you have? CJ, you look like there's about to be a question. Okay. If it goes away, Ask me again. If the answer flies out of your head, you can just yeah, okay. All right, so on to the equivalent one-body problem. And I've never done this before, but you know what? I think, because it's going to get tiresome to keep writing the equivalent one-body problem, so let's call this the E1BP. The E1BP, the equivalent one-body problem there. Okay? So we've got the reduced mass, mu equals m1 m2 over m1 plus m2. Well, note that this says 1 over mu is m1 plus m2 over m1 m2, which is 1 over m1 plus 1 over m2, right? Because m1 over m12 is 1 over m2, and m2 over m12 is 1 over m1. So 1 over mu is 1 over m1 plus 1 over m2. In other words, in determining the reduced mass, the masses add and reciprocal. Does this remind you of anything? From a different branch of physics, as it were. Yeah, and what does this remind you of in terms of electric circuits? Yeah, so resistors wired in what configuration have the property that 1 over the total resistance is 1 over R1 plus 1 over R2? What produces that? Not series, there they add. Parallel. Parallel, yeah. If I've got R1, R2, that's equivalent to having a single resistor, right? R equal, where 1 over R is 1 over R1 plus 1 over R2. Or also you can just say R is equal to R1 over 2 over R1 plus R2. So just by coincidence, the equivalent mass behaves the same way in relative to the two masses involved as the equivalent resistance does for resistors in parallel. And remember, if you have resistors in parallel, the smaller resistor dominates, right? In other words, if one of them is way smaller than the other one, the equivalent resistance is practically just the smaller resistance, because kind of all the current practically goes through that one. Yes?
Are you saying equivalent mass as the same as reduced mass?
No. Here I am saying, I'm not calling it an equivalent mass. I'm just saying that, so if I accidentally said equivalent mass, that was a mistake on my part. What I really want to say is the reduced mass is related to M1 and M2 the way the equivalent resistance is related to R1 and R2 for resistors in parallel. Now, does this mean that the masses are wired in parallel? No, of course not. It does. Okay, sorry. Yes, it does. Yes, this is a mass circuit, and the masses are in parallel. I quit. Yeah. Okay. So this is the reduced mass. So this was all on the side. Aside. What was I going to say? Is that an H? Was I starting an H word? What is it doing? Anyway, I'll just start again. The reduced mass orbits a fixed mass So in other words, a little weirdness is in the equivalent one-body problem, mu orbits capital M, and capital M is just sitting there, which is not what would really happen if you had mu and capital M, because capital M would be moving under the influence of the gravity of mu. But in the equivalent one-body problem, capital M sits at the center of mass and is locked into place there, nailed in place with magic space-time nails. So that's a little unphysical, but it doesn't hurt. We understand what we're doing. Or it's a fixed mass, M, capital M equals M1 plus M2. For convenience, we put M at the origin, at the center of mass. We put capital M at the origin and at the center of mass, because that's what we decided we were going to do, is put this is right along with the center of mass at the origin. And so the idea is, there's capital M, and here's mu orbiting capital M, where capital, it's on an ellipse with capital M at one focus of the ellipse. And so that vector right there, R, is in the real system, R2 minus R1, the displacement vector of M2 relative to M1. So mu is located with respect to M the same way little m2 is located with respect to M1. The location of mu with respect to capital M is the same as the location of M2 with respect to M1 in the real system. At all times. Or in other words, the position vector of mu it's not a vector. The position vector of mu is R is equal to R2 minus R1, and mu's velocity, its velocity is V equals R dot equals R2 dot minus R1 dot equals V2 minus V1, which is the velocity of M2 relative to M1. It's if you are sitting on M1, basically if you are riding along in the real system on M1 and following the location of M2, you'd see the same thing as in the equivalent body problem, riding along on capital M and looking at mu. You'd see exactly the same thing. But in the real system, riding on M1, you're in a non-inertial reference frame because you're orbiting the center of mass. But in the equivalent one-body problem, capital M's at the center of mass and mu is orbiting that. So this is the velocity of M2 relative to M1. What questions do you have? It's a good thing, I think, that chalk dust is not toxic. My lungs must have a little coating of chalk dust in them, which I'm guessing is better, I could be wrong, better than a thin coating of whiteboard marker dust. It's another reason I'm not a big whiteboard person. I just feel like this is probably better than that. I'm just guessing, yeah. All right. The relative orbit has semi-major axis equal to the sum of the semi-major axes of the two actual orbits. And as we had mentioned before, its eccentricity is the same as the eccentricity of the two actual orbits, because those are the same as one another, and the relative orbit has the same eccentricity as it does. So in other words, going back to this system here, pick one of these to be M1 and the other to be M2. So let's call this one M1. The little one here is the little more massive one is M1. I wouldn't have to do this, but I am just choosing it. Here's M1. That's M2. Imagine you're riding along on M1 and tracing out where M2 is relative to you at all times. You put yourself at the origin, trace out where M2 is relative to you at all times. You will have traced out the orbit of mu relative to capital M in the equivalent one-body problem. That's the idea here. Okay? With the C of M at the origin, so in other words, we're making capital R that vector B0 by putting the center of mass at the origin. We have, like we said before, M1 R1 plus M2 R2 is equal to 0. And we can use the fact that R2 is R1 plus R, right? Because R was R2 minus R1, so R2 is R1 plus R. R being the relative vector between them, the relative separation, R2 minus R1. So put that in here. Put that in for R2, and we get M1 R1 plus M2 R1 plus M2 R is equal to 0. And now we can solve for R1 in terms of R. So that says R1 is equal to minus M2 over M1 plus M2 times R. Or in other words, we could call that minus M2 over capital M times R, if we like. So notice what this is saying is, if we know R in the equivalent one-body problem, and I want to know what R1 is, I just plug into this formula. If I want to go back to the actual system and figure out what R1 is, where's the actual R1, just use that formula. And that'll tell us that. And similarly, if we do the same thing for R2, we find that R2 is equal to plus, in this case, M1 over M1 plus M2R, or in other words, it's plus M1 over capital M times R. So if I know the value of R, the relative displacement, these two formulas can give me the values of R1 and R2 in the actual system. Or alternatively, since the equivalent one-body problem, we've got capital M and mu in it, let's put these in terms of capital M and mu. So with mu is equal to M1, M2 over M1 plus M2. Why, that's going to give us that R1 is equal to minus mu over M1 times R, and R2 is plus mu over M2 times R. And these are both very much box-worthy relationships there. Yes?
Is a relative R always a big carrier object?
No, so you mean like the little r there?
Because you have M2 with R, relative R. On your left, the bottom equation.
Here? So I just, so it's up to you which object is number one, which object is number two. And so it doesn't matter whether M2 is larger or M1 is larger here. The math is exactly the same. It doesn't care what M1 and M2 actually are here. So you pick one of them to be M1 and the other one to be M2. And R is always that vector that connects M1 to M2 like that. But you can pick either one to be M1 and the other one to be M2.
Yes, but could you explain the bottom equation again?
This one right here? This right here? Yeah, so by definition, R is R2 minus R1. It's the location of 2 relative to 1, right? And so therefore, we can say that R2 is equal to R1 plus R, just moving the R1 over there. Then I take this and plug this for R2 in that expression. So then I get M1R1 plus M2R1 plus M2R right there. So it's just an algebraic substitution. And now I can solve for R1 in terms of R, because this is saying M1 plus M2 times R1 is equal to minus M2 times R, and then I just solve for R1. Mm-hmm. Yep. What other questions do you have? What is that? What, that? Oh no, that's not an L. It's an E. Right. This is, so I'm saying here, the eccentricity of the relative orbit is the same as that of orbit 1 and orbit 2. Yeah, yeah, that's not an L. Right. Yep. Is what that is. All right. And if you think otherwise, I mean, what the hell? Yeah, okay, so, all right. Can I erase this? It's going to... What's that? No, okay. Can I erase this stuff? No, okay. It's new. Instanote was no. It's Instanote technology, right? Yes. No. Right. Yeah.
Yes.
There we go. Yeah.
It's
okay. So I can erase this now. Okay. Okay. All right. So now let's do something cool here. I mean, it's all cool, but let's convince ourselves that this is legit, that we would want to do this. So now we rewrite the energy rewrite the energy of our system, sum of the kinetic and potential energy for the actual two-body problem, the real system that we're studying, and we'll show that in terms of one-body quantities, it's exactly what we would want. It's exactly what we would expect if the one-body problem really truly is equivalent to the two-body problem. So now we rewrite the energy. Capital E is, so it'll be the sum of the two kinetic energies, 1/2 m1 v1 squared plus 1/2 m2 v2 squared. And I'll go ahead and, often we will, when I say something like v1 squared, well, that's v1 dot v1, right? Which is the magnitude of v1 squared, which we will then just say is v1 squared. So sometimes I put a vector over to emphasize this is, when I say v1 squared, I really mean v dot itself. Plus 1/2 m2 v2 squared minus g times m1, m2 over the distance between them, but the distance between them is the magnitude of the vector r2 minus r1, right? In other words, remember, I got m1, I got m2, I have their relative vector r equals r2 minus r1, and if I want to call that r the distance between them, well, r is in fact the magnitude of that relative displacement vector. So instead of just m1, m2 over r, I'm saying the magnitude of r2 over r2 minus r1 down there. We're going to rewrite the energy in terms of quantities relevant to the E1BP. In terms of quantities relevant to the equivalent one-body problem. That felt so good to write that instead of the equivalent one-body problem. I mean, I don't mind saying it, but good God. Okay, so from above, we have, remember we said R1 was equal to minus mu over M1 times R. And so that's going to say take a derivative, take a dot, take a derivative that says V1 is equal to minus mu over M1 V, just by taking a time derivative of that. And similarly, we've got R2 was equal to plus mu over M2 R, and that says that the velocity of actual body 2 is equal to mu over m2 times the relative velocity v of m2 relative to m1. We can do that. So putting those in to our formula, says E is equal to 1/2 m1 times mu squared over m2 squared v squared plus 1/2 m2 mu squared over this is an m1 right there, m1 squared v squared plus 1/2 m2 mu squared over m2 squared v squared minus g, and then m1, m2 is the same thing as m1 plus m2 times m1, m2 over m1 plus m2 over r, because we noted that 1 over the magnitude of r2 minus r1 is just 1 over r, the distance between them. So I've just chosen to rewrite m1, m2 as m1 plus m2 times m1, m2 over m1 plus m2. You can't stop me from multiplying and dividing by m1 plus m2. But wait a minute. In terms of the equivalent one-body problem, what's m1 plus m2? Capital M, right? That's capital M. And what's m1, m2 over m1 plus m2? That's mu, right? So in place of gm1, m2 over r, we get g big M mu over r, just like we would like. That's like if I just had two bodies, capital M and mu gravitating, their potential energy would be minus g m mu over r. And then for this piece right here, for the kinetic energy piece, we've got factor out 1/2 mu squared. So we've got 1/2 mu squared times m1 over m1 squared is 1 over m1. And m2 over m2 squared is 1 over m2. And then all that times v squared minus gm mu over r. But wait, remember when we were talking about resistors? 1 over m1 plus 1 over m2 is 1 over mu is 1 over mu. And so we've got 1/2 mu squared over mu times v squared minus gm mu over r. In other words, our grand result, E, is 1/2 mu v squared minus gm mu over r. Ta-da! Ooh-ah! In other words, the total energy of the system, kinetic plus potential, is 1/2 mu v squared minus gm mu over r. Why, that's the kinetic energy of the reduced mass, and that's the potential energy of m and mu interacting under gravity with one another. The equivalent one-body problem in terms of energy really is equivalent, in other words. It really is giving us the same thing. But wait, there's more. Next time we'll show how the angular momentum works out. And that'll be just as awesome, and we're just going to go nuts with that. It's going to be glorious and awesome and wonderful and everything, which gives you reason to carry on over this weekend, right? If there's any like, oh, I'm just not feeling it right now. But wait, next week on Monday, I get to learn about angular momentum, and I just can't even keep talking here. So, all right, so stay tuned. Same time, same channel. We'll continue.